And now, I'd like to introduce our presenter. Jason Coder received his BSEE and MSEE degrees from the University of Colorado Denver in 2008 and 2010, respectively. Mr. Coder currently leads the Shared Spectrum Metrology Group in the National Institute of Standards and Technology's Communication Technology Laboratory. During his tenure at NIST, Mr. Coder has worked in fundamental EM measurements, EMC, and antenna measurements. His current research focuses on developing new measurement methods for spectrum sharing, wireless coexistence, and interference. Mr. Coder currently serves as the chair of the ANSI C63.27 Working Group on Wireless Coexistence and the chair of ANSI C63 Subcommittee 7 on Spectrum Adequate. So, without further ado, let's turn our attention to wireless coexistent measurements and challenges. Why can't we all get along with Jason Coder?
Thanks for the introduction. Let me share my screen. Great. Thanks everyone for attending the webinar today. Hopefully we'll have some time to get into some of the questions that are submitted via email towards the end of the talk. And then I've also included my contact information on the last slide, and I encourage folks to send me questions if they have them. First, I want to acknowledge some of the folks that I work with and some of the collaborators that I work with. NIST's work on wireless coexistence is certainly a team effort, both internal and external. Dr. Yao Ma, Dr. Susanna Mosley, Dr. Jake Rizak, Aziz Cord, Chris Hess, and others have made lots of contributions to NIST's coexistence work as well as external efforts that we have. And you'll see some of their work here today. I also want to acknowledge our collaborators at the Food and Drug Administration and the University of Oklahoma. They've been longtime collaborators with our wireless coexistence efforts and making contributions in the community as well, and you'll see some of their work today here as well. Up front, I just want to point out that this presentation is for informational and educational purposes only. I will talk about some of the relevant standards that apply to wireless coexistence, but please, if you have specific questions about the standard, refer to the standard itself, or even if necessary, submit a formal interpretation request to the standard. Just a quick outline of what I'll cover today. I'll start by just kind of introducing the concept of coexistence in general, and try to get people comfortable with what coexistence is and with what it isn't. I'll talk about the need for testing, kind of go through the need for why people are interested in doing coexistence measurements at all. I'll talk about the need for standardization. And then I'll talk about some tools that we have in terms of modeling and measurements to try and understand coexistence challenges and understand device performance. And then I'll conclude by talking about some future topics and coexistence applications. So what is coexistence? Coexistence is kind of an interesting and somewhat new concept when it comes to wireless devices. And the question that we're interested in is, how well can my device perform amongst other devices that are operating around me? We focus on the wireless communications link, and you can kind of think about this as being analogous to a lot of people talking in a room, maybe at a party or in a restaurant. And everybody's kind of in smaller groups having their own conversation, and you can still mostly make out what the person you're talking to is saying. But even if you're all talking in a reasonable voice, there can still be impacts. Somebody talking next to you, you might miss a word or two of what your spouse is trying to say, or someone may not hear you clearly. And so coexistence kind of pulls on this thread of, even if everyone is following some given set of rules, that there can still be impacts between devices or between applications. And so coexistence testing is really about trying to understand how well my device does or will perform, even though there's lots of other wireless devices operating nearby. I'll start with a simple example here of a Bluetooth communications link, and coexistence applies to lots of different systems, as we'll talk about. Kind of throughout this presentation, I'll use this Bluetooth and Wi-Fi example that I talk about here, but again, it's just an example. So consider a case where we have a sensor relaying information to a central node via Bluetooth. So this could be as simple as maybe a watch that's monitoring heart rate, and it's relaying that information back to a cellular handset, perhaps. And in coexistence, we want to understand how this Bluetooth device and link will operate under different circumstances. We can think about this in a very simple case of if the Bluetooth device and its central node are in free space, maybe in an anechoic chamber, with no other electromagnetic activity present, I think we would all feel comfortable understanding how that link would work, how it would function, what the limits of that link are. That might be measured in how far apart we can have the two devices. So people have a pretty good understanding of how well that would work in that case. But now if we introduce a Wi-Fi network into that same area, now it starts to get a little bit interesting. Even though it's still free space, now we have a Wi-Fi network that's also operating in the same frequency band. What impact does that have on our Bluetooth device? Will our Bluetooth device still be able to perform as we expect? What are the limitations now that there's another Wi-Fi network that's completely unrelated to our device, but it's operating nearby? So do we understand how well our device will work in that scenario? And then finally, taking that a step further to, say, a hospital environment where you typically have a very congested, unlicensed ISM band. You have many other networks and protocols operating in the environment. Can we come up with a way to understand how our simple Bluetooth device and its companion device perform in this environment? You can imagine that it's a much more complicated process now that we have to account for all of these other networks that are operating, as well as the physical hospital environment itself. It's no longer free space. So coexistence really gets at this idea of, can we quantify how well our Bluetooth device performs in each of these environments? And we'll kind of go through some tools that we have to answer that question. Everyone has a strong desire to understand how well a wireless device will perform in its environment before it's deployed. We'd all love to have this crystal ball that would tell us what's going to happen when I introduce my device into a given environment. End users, manufacturers, system administrators, regulators, they'd all like to be able to understand what's going to happen when they put their device in a given environment from a wireless coexistence perspective. And if we think about what tools do we have to answer that question, we can kind of separate them into two categories. The first category is modeling, and this is sometimes referred to as probability of coexistence or likelihood of coexistence, and we'll talk more about those in some upcoming slides. And then we have a set of measurement methods where we can do some physical laboratory experiments to try and answer this question about coexistence. But we wish that we had more tools. We wish that we had better tools. The tools that we have today, give us a lot more information than no tools at all, but it's still an active area of research, and I'll talk a little bit about some of our efforts in those areas. One of the most common questions that we get about wireless coexistence is people will say, isn't this interference? This is the same measurements we've been doing for decades. What's really the difference here? And interference is the unintentional effect of energy emitted by a source, usually in equipment that is not intended to receive RF EM energy. Whereas coexistence testing involves devices that are intentional radiators and receivers. So in coexistence testing, we're focusing on how the device communicates and how it intentionally radiates and receives energy. Interference testing typically deals with what happens when I subject a device to some unrelated signal in the environment? Will my device still perform in the presence of that energy? Coexistence really tries to look at how well a device will maintain its performance, in its intentional performance. The other common question that we get is, isn't this only an unlicensed problem? Isn't this really just a problem that's confined to the unlicensed bands? And the answer is it's not. Anytime that you have two systems that are co-located or adjacent in time, frequency, or space, you run the risk of having a coexistence issue. Some examples of that are the AWS-3 frequency band that was recently auctioned off, or I guess a few years ago now, auctioned off in the United States. This is a situation where commercial carriers need to coexist with some incumbent DoD assets. There's also the 3.5 gigahertz band in the United States, which is known as the CBRS, Citizens Broadband Radio Service. And there's again a coexistence issue with DoD assets where commercial entities can use that frequency band until a DoD asset needs it, and then users need to vacate the spectrum. There's also challenges up in the millimeter wave frequency bands at 24 gigahertz, where you have concern about coexistence between potential 5G LTE deployments and existing weather satellites. So coexistence covers a wide range of frequency bands, covers a wide range of applications, and it can be in scenarios where you have coordinated sharing or uncoordinated sharing. Coordinated sharing would be things like the 3.5 gigahertz CBRS band, where you have a spectrum access system that is managing access to the radio spectrum, or it can be uncoordinated in the case of the unlicensed band, where you have various devices and protocols that are trying to sense the channel and not directly interact with each other. Coexistence covers a wide impact. Consumer devices, medical devices, Internet of Things, vehicles are seeing an increased number of wireless devices. Military and satellites are also two areas that are impacted by coexistence, and we just talked about a couple examples of those. Coexistence measurements, as I've kind of alluded to up to this point, have some fundamental challenges associated with them. If we think about just conceptually how we would try and measure coexistence, one of the first things that you'll probably think about is, what's the unit of coexistence? What's the SI unit here? Is it a volt? Is it an ohm? Is it an amp? Right? So what quantity are we actually measuring in a coexistence test? Thinking at a slightly higher level, thinking about, well, is it signal power, either the intended signal power or the unintended signal power? Is it maybe some data throughput? Or is it some frame rate in the case of video, or audio quality in the case of voice? And is it even the same quantity for each test? Thinking past that a little bit, we have to think about what constitutes a pass or a fail on a coexistence test. And if I do a coexistence test in my lab and you do one in your lab, will we get the same answer? How do we design a coexistence test that's repeatable and rigorous so that lots of people can do testing and get answers that are comparable? So these are some of the fundamental challenges that I'll try and illustrate here as we go throughout this presentation. A quick example here about measurands. In the last slide, I mentioned talking about throughput or frame rate or audio quality. And my goal here with this slide is just to show that it does make a difference. So this is an example from a Wi-Fi and Bluetooth test that we did in our lab. And here the Bluetooth low energy and Wi-Fi links are co-located in frequency. And what we see is that on the x-axis of this plot, as we increase the Wi-Fi power, we see that the received signal strength indicator, as reported by the BLE system, is fairly constant. So despite there being an increase in energy in the frequency band and in the channel that the BLE link is trying to use, it's not reporting any change. Even though if we were to look at throughput or we were to look at some other metrics, we would see that as the Wi-Fi power increases, the Bluetooth performance is actually degrading. And so here is an example again to just show that the metric or the measurand that you choose in your coexistence measurement does have an impact. So let's talk a little bit about the need for coexistence testing. In general, it's to answer this question of how will my device perform, but coexistence testing can have multiple purposes. It can be to develop guidelines for ensuring reliable operation, estimating the user experience, or identifying cases where the system fails to coexist. Those are all pre-deployment coexistence tests. Those might be in a development stage of a product where a company is trying to get an idea of what the user experience will look like if they're using their ISM device in a crowded environment. There's also post-deployment coexistence tests. So you could deploy a device in a hospital or in a given environment, and the manufacturer could be getting complaints or reports of failure, and you could do a coexistence test to try and replicate that scenario after the fact to understand what's going on. Specifically for medical devices, one of the things that the FDA did in 2013 was they issued a guidance document on testing for RF wireless devices. And one of the things that they said was that if the RF wireless medical device is expected to be used in proximity to other RF wireless in-band sources, the FDA recommends addressing such risks through testing for coexistence of the device and the system. And so this is good guidance with the proliferation of wireless devices. I think we can all agree that understanding how a medical device in particular performs in an environment like that is valuable. But at the time, in 2013, there weren't a lot of measurement protocols, and there certainly weren't any measurement standards in place to give people an idea of how to tackle wireless coexistence. So now we start to look at the need for standardization. So we've covered that there's many possible parameters in play here, many different KPIs or metrics or measurands that could be involved. Standardization would really allow for kind of an apples-to-apples comparison between labs and measurements. Standardization will also provide a generalized procedure that could be adapted to meet a variety of frequency bands and technologies, and it would enable regulators to efficiently assess coexistence testing and results and try and understand what a product being submitted for approval, what its performance actually is. So one of the early coexistence standards was IEEE 1900.2. It's a recommended practice for analysis of coexistence between radio systems, and it was developed between 2005 and 2008 by a working group. It's up for revision in 2020, and I've heard several different proposals for how that standard could be revised or updated or taken in different directions. But right now, it's geared towards network operators and system administrators. It provides kind of a mindset for thinking about coexistence if you are deploying new networks in a space that you manage, and understanding the risks associated with that and some ways to mitigate those. It doesn't get into actual measurements or ways to quantify coexistence. So it was a great document to get people to start thinking about coexistence as a concept and start trying to understand and mitigate it. But it still left a little bit of a gap in that people need measurements and wanted ways to quantify coexistence. So the other standard is the ANSI C63.27 standard, and this is the American national standard for the evaluation of wireless coexistence. We have seen it used across the world for coexistence testing. It was developed by a fairly large working group. There were 90 people in the working group across industry, government, and academia. And initially, this working group was driven by the medical device community, kind of in response to that 2013 FDA guidance, where people said, okay, measuring coexistence is a good idea, but how should we do it? And so a lot of folks came together in this working group to kind of work out a set of measurement methods and a standard way of measuring coexistence. Later on in the working group, there got to be a lot of other folks involved, other consumer devices, other government agencies, other universities, as I think people started to realize that coexistence is really a large problem. The first version of it was published in 2017. There's a revision to the standard that's going through balloting, and it's expected late this year or early next year. And we'll talk some more about what's contained within this standard. There's a few key components. It starts with the evaluation of your equipment under test and determining this idea or this concept of a device's wireless functions. So what's the functional wireless performance of a device? And we'll talk more about what that means specifically. The standard also walks you through determining what metrics will be used to monitor the functions. So the standard doesn't specify that you have to use throughput or you have to use some signal power. It instead provides a framework for letting the person doing the testing select those metrics and how to do so in a sound way. It also talks about the level of testing needed to sufficiently evaluate the device. The standard recognizes that some wireless devices that will go through a coexistence test may be for recreational use or casual consumer use, and other devices may have a wireless link that relays life safety or critical information, and those devices need a higher level of testing associated with them. So the standard does provide for that. It also goes through some generalized test methods. These are either conducted or irradiated test methods. The guidance that it provides is technology agnostic. So there's nothing in the body of the document that restricts coexistence testing to Wi-Fi and Bluetooth or Wi-Fi and LTE or any other two protocols. It really provides a general framework that can be used to assess coexistence between any two systems. That said, in response to kind of popular demand and the working group's assessment of what some of the most popular coexistence tests would be, there's a normative annex to the standard that does go through some technology-specific guidance. For example, it covers Wi-Fi EUTs operating in the 2.4 or 5 gigahertz band, as well as Bluetooth devices under test. Something that's coming up in version 2 of the document, as I said, is working its way through balloting, is the sort of a treatment of LTE and Wi-Fi coexistence testing. The standard also includes an evaluation of measurement uncertainties. This is going to vary a little bit based on the exact test method that's selected, but the standard does try and walk people through understanding uncertainty of a coexistence test. This is something else that's really been trying to reinforce and improve coming out for the second version of the standard. There's also a few optional extensions, including risk analysis, which is intended for medical device applications. And then there's also a calculation of the likelihood of coexistence, or this modeling aspect that I talked about earlier. So the standard has two key objectives. One of them, and this is a quote from the document from version 1, is for assessing the ability of the equipment under test to successfully maintain its functional wireless performance in the presence of intended signals that are likely to be found in the same operating environment. And that's kind of a mouthful, so we'll break that down here coming up. Another objective is the results of this test may optionally be used to compute the likelihood of coexistence or as an input to a risk assessment. And again, risk assessment typically refers to a medical device risk assessment. So you could certainly use the results of a coexistence test to assess risk in other ways. So let's look at the first part of that objective statement. For assessing the ability of the equipment under test to successfully maintain its functional wireless performance in the presence of unintended signals that are likely to be found in the same operating environment. So we have this, we have different pieces of equipment under test, and they have different applications, and that's going to yield different metrics for each coexistence test. And so some examples of this might be some applications might need to rely on bit error rates being less than some threshold, while other applications may need to rely on dropping some number of frames that's less than a specified value. So for each equipment under test, we can define its functional wireless performance, which is the subset of its total functionality that both uses the wireless capabilities of the EUT and would result in unacceptable consequences if degraded or disrupted. So we're not testing everything in the device, we're only testing a subset of its total functionality here. Let's look at the second half of the statement. In the presence of unintended signals that are likely to be found in the same operating environment. This is a difficult one because it raises the question of what do we know about the operating environment? What signals will be present and how often will they be present? And at what power and amplitude will they be present? And what if my device is going to be carried by a person that, walks through, starts off in their home, goes to an office environment, goes to an airport, goes to a hospital maybe, goes through a bunch of different wireless environments. And so this is really a difficult question here because there's a fairly limited number of surveys of different environments. And when you start looking at those surveys, you need to start looking at what method did they use for surveying it, and things like sensor distribution and measurement technique. And so this environmental survey area is an active area of research for several different entities, as well as a way to try and bring all this data together and make it more accessible for the community. So here what I've shown is a snapshot of the spectrum of a hospital environment. Along the x-axis, you've got the time of day, so you've got a 24-hour capture here. And then on the y-axis, you've got a measure of channel occupancy. And what they're looking at here is they've got 3 different traces for the 3 different Wi-Fi channels that are non-overlapping, and you can see the activity as the day goes on. And you might say, well, there's a lot of activity between midnight and 6 a.m. at a time when I didn't expect any activity, and it may be the case that that's the time when all of the hospital IT systems choose to push updates to their devices and their computers on their network. But you can see that this information is very valuable because it gives you some idea of what your device will encounter, and that really informs what kind of coexistence test you can do and ultimately helps improve the results. So there's kind of 2 approaches to coexistence here. We can group them into 2 categories. One is the modeling category and one is the measurements category. We'll talk about the modeling category first. In the ANSI document, this is referred to as the likelihood of coexistence. And the idea is that if we know certain things about the device and about the operating environment, can we predict its performance? It's included as an optional part of the ANSI standard. It's designed to be a framework. As we'll see in the next couple slides, modeling here can get pretty complicated pretty quickly. And so for that reason, it's just an annex in the standard. Some of the necessary inputs here are the strength and quality of the intended signal. So that might be the signal from my central Bluetooth node that we talked about in the first couple slides. You also need some information on what kind of signals and fields you're going to encounter in the operational environment. And you need to try and account for any anticipated variations in the network or outside the physical layer that may impact performance. So is there something else that may be going on in the system that would cause the throughput to drop? Does the network slow down for some reason and cause the throughput to drop and thus cause your device to fall below some threshold? If the network causes a failure, that's a different kind of problem than wireless coexistence causing the failure. So that's something that you should try and account for in the model. And we also need to understand the level at which a failure occurs. And this can come from testing. As with any model, the quality of the prediction depends on the quality of the inputs. If you put garbage in, you're going to get garbage out. And so I encourage folks to proceed with some caution there. There's 2 different types of modeling methods available. There's a direct measurement method, which is the more simple of the 2, and then there's a model-based measurement method. The direct measurement method relies only on measurement data to estimate the likelihood of coexistence. It's not really a mathematical complex model like we'll talk about in a second. It's not parametric. A simple example is that if you do a coexistence test and your goal is to maintain 1 megabit of throughput on some link, and you do 100 coexistence tests and you find that you're able to maintain that link and that threshold 60 times out of 100, then your likelihood of coexistence becomes simply 60%. The model-based measurement method is more complicated. It requires modeling of the whole system and some uncertainty analysis combined with measurement data. You can see in the diagram below, there is kind of one track for modeling analysis along the top, and then another track along the bottom for measurements, and then they get compared and validated together to try and improve the model. One needs to derive system observation and measurement equations in this case, and you really need to capture the interaction between parameters. So this can get very complicated very quickly and may include things that you don't know. You're not sure of how two parameters will interact. However, the model has some advantages in that if you're able to model things, you can account for dynamic changes. So you can look at how things change in the environment. And you can also look at hypothetical changes. So because you're using a lot of theoretical constructs and models here, you can say, well, what happens if I tweak this parameter a little bit, and you can look at the results. So modeling can be a very powerful tool for looking at scenarios that haven't become a reality yet. And we'll get into some of that modeling later on in the application section. The models, as I have said, can become very complicated, and you may need to include more than just the physical layer interactions. You may need to include things like the MAC layer interactions between parameters. Likelihood of coexistence calculations are still an active area of research, but again, modeling does have some benefits. It enables coexistence to become proactive instead of reactive, and so we can ask the question about how do we design protocols to inherently facilitate coexistence, or what are some ways that we can look at deploying existing networks in a different way to facilitate coexistence. So it allows us to start looking at some of those questions. As these models become increasingly complicated, we can start to leverage things like machine learning, neural networks, et cetera, to track multiple metrics throughout the system. And some of my colleagues at NIST have a publication on this coming out at a conference, I believe, in the next month or so. So now let's talk about the other approach to coexistence, which is a measurements-based approach. Measurements face a similar challenge. How well do we know the deployment environment? What do we know about it? If we knew exactly what signals a device was going to encounter during deployment, we could plug that into our coexistence test, and our coexistence test would be perfect. Unfortunately, it's hard to say exactly what we'll encounter in the real world, and so this adds a little bit of uncertainty into our coexistence measurement. The other thing to keep in mind for coexistence measurements is that the systems that we're testing are very complicated, and wireless communication systems are becoming increasingly complicated. So we need to ensure that a test is being conducted as we expect, and this is why it's always a good idea to use a spectrum analyzer or vector signal analyzer to monitor things during the test to ensure that it's being performed as you expect. Coexistence measurements can be performed at any stage, either in the prototype stage, verification validation stage, or even in the post-deployment stage, as we talked about earlier. No measurement method is perfect. As I mentioned, the ANSI standard outlines 4 different measurement methods, and there are others available if you search around. But each has its own set of assumptions and compromises. And you kind of have to think about how close to reality is it. With coexistence testing, there's no one-size-fits-all measurement method. There are pros and cons to each one. For example, with conducted testing, that's great if you're just doing prototype testing and if you have access to conducted ports, but a lot of devices these days are fully integrated, sealed up, basically black boxes, and you don't have access to any conducted ports. So that kind of pushes you towards radiated testing. As I mentioned, there's 4 different measurement methods that are discussed in the ANSI C63.27 standard. They're a conducted method, a multiple chamber method, which entails putting your device or your equipment under test in one chamber, having it an antenna at the top of that chamber, connect to some cabling, And then in another small radiated chamber, you have your companion device, and then you can insert an unintended signal or unintended network in there as well. That's a great option for people or for cases that are looking for a lot of control of the propagation channel between the two devices. Some people will insert a channel emulator in between those two chambers, for example. Another measurement method is the radiated anechoic chamber. This is sort of a traditional, just you put your test in an anechoic chamber, everything is radiated, and you perform your test there. There's also a radiated open environment method where if done properly, you can actually do the coexistence test basically in situ. You can do it in the deployment environment. And that's the goal behind this radiated open environment method, is that particularly for post-deployment cases or for cases where people were anticipating a highly reflective environment, the working group wanted to allow them to use a tool or a measurement method that would help them assess coexistence in that case. And so that's the idea behind the radiated open environment test. There's a little bit of extra caution, of course, that has to be used there because you are in an open environment. You know, there may be other ambient signals that are in the environment, and you need to ensure or at least understand what impact those are having on your coexistence test. People are free to choose between the test methods. The ANSI standard doesn't make any restriction on which test method someone is required to use. It typically depends on what connections are available to the test device. Again, sometimes conducted ports aren't available, and thus you need to go with radiated testing. It depends on available facilities. Sometimes someone interested in doing a coexistence test may not have an anechoic chamber available, so that pushes them to one of the other methods. Testing budget, desired accuracy, or stage of development can also play a part in which of the 4 test methods you end up selecting. Ideally, regardless of which of the 4 test methods you use, you should get the same result. This is a significant challenge, and there was a lot of work done in the working group to try and make sure that that was the case, that someone doing a conducted measurement would get results that were comparable to someone doing a radiated measurement. It still is a challenge, and there's still a lot of work there that needs to be done to try and improve that. But this is kind of the drawback of having many choices. I think that there's a lot of different ways to do a coexistence test. There's a lot of different acceptable ways to do a coexistence test. We just needed to do the work and make sure that the test is done in a way that's repeatable across the test methods. We've talked a little bit about this idea of measurement uncertainty, and in coexistence testing, we've introduced this other term called evaluation uncertainty, which is a little bit different. So measurement uncertainty is sort of what most people are used to when they think about uncertainty. It's a parameter associated with the result of a measurement that characterizes the dispersion of values that could reasonably be attributed to the measurand. So if I'm trying to measure a voltage on a voltmeter, you know, the voltage may in fact be 5.0000 volts, but for a variety of reasons, there'll be a distribution associated with that. There'll be some uncertainty associated with that as you try and measure it. The same applies in coexistence. Whatever measurand you're interested in, there's some uncertainty associated with your ability to measure it, whether it's throughput or signal power or frame rate. There's some uncertainty associated. There's some dispersion there around your ability to measure that. Evaluation uncertainty is a different concept. Here, the standard defines it as an estimate of the range of values that can reasonably be expected in the projected field experience predicted from laboratory test results. So this idea of evaluation uncertainty tries to get at the fact that if you do a conducted test, for example, your test is not going to include some factors that could influence the outcome of your coexistence test. For example, antenna pattern, or MIMO, or beamforming. Those things are very difficult to account for in a conducted test. So you can do a conducted test, but you should realize that there are things that are left out of that test that may be important. So you can think of evaluation uncertainty and measurement uncertainty as kind of a trade-off. you can do a conducted test where you typically have a low measurement uncertainty. It's easier to measure quantities in a conducted environment, but you have a high evaluation uncertainty because it may be more difficult to replicate your deployment environment from a physical perspective. And the opposite is true with a radiated open environment test. There, your evaluation uncertainty may be very low because you may be using the deployment environment itself. On the other hand, it may be difficult to measure signal power, for example, in that radiated setup. So it is a little bit of a trade-off. The standard requires that test reports have a measurement uncertainty budget, but evaluation uncertainty is something that should be considered. It's not, at this time, there's no evaluation uncertainty budget per se. As I mentioned, the core of the ANSI standard is technology agnostic. You can use the 4 test methods, and you can use the framework for any set of systems that you're interested in assessing the coexistence for. However, in Annex A, there is some technology-specific guidance for, like I said, the most common scenarios. So this is Bluetooth and Bluetooth Low Energy equipment under test, 2.4 and 5 gigahertz Wi-Fi, DECT devices, which are typically cordless phones operating in the UPCS band, and also LTE LAA devices, which is coming soon with the second revision. I also mentioned earlier that there's this idea of tiered testing where devices that are less critical require less testing than devices that are more critical. And an example of that is shown here for Bluetooth devices. So if you have a device that isn't very critical, it would fall under Tier 3. And in that case, the recommendation is that you test that with a single 802.11n channel. However, if your device is most critical, Tier 1, you need to do Tier 3 and Tier 2 testing, plus additional 802.11n and adjacent band LTE configurations to really demonstrate that your device is going to continue to maintain its performance even in the most congested of co-channel and adjacent channel conditions. Some people like to think about coexistence testing in an iterative sense, and you can certainly do that. Some people prefer to set up a coexistence test, and instead of following sort of the tiered approach to testing, they'll just test it until it breaks. And so this is kind of the, I'm going to turn that signal up to 11 and see where it fails. And that's certainly an acceptable way to do testing. The cases that are outlined in Annex A were designed to be kind of reasonable worst case test specifications. And this is always a debate in standards development, whether or not you go for the true worst case or whether or not you go for some average or somewhere in between. So in the ANSI document, the mindset was a reasonable worst case test specification, but certainly there are people that want to answer the question of, at what point will my device no longer coexist, no longer maintain its functional wireless performance? And maybe in my Bluetooth Wi-Fi example from earlier, you just keep turning up that Wi-Fi signal power, and eventually you find that Bluetooth link drops when the Wi-Fi signal power is plus 30 dBm. And then you say, okay, well, the likelihood of encountering a plus 30 dBm Wi-Fi signal in the real world is admittedly extremely low. And so then you have some assurance and a good feeling about how your device is going to perform. Some examples of Wi-Fi test deliverables. So you do a Wi-Fi test and you get this data. What does it really mean? You could use it to specify the minimum distance between maybe your Bluetooth device and a Wi-Fi access point, or perhaps the maximum distance between your Bluetooth device and its companion device, its central node. Or you could use it to kind of set a threshold where your DUT needs to change channels or make some kind of adjustment in order to ensure that it maintains its functional wireless performance. So now I'll go through some examples of applications and future topics. There are lots of applications and future topics of coexistence. The ones that I show here are ones that are also active areas of research for NIST. So here, this is an example that my colleague, Dr. Yao Ma, has worked on where We did some coexistence modeling, some likelihood of coexistence calculations to look at how LTE and Wi-Fi would interact. So there was some questions, some controversy a few years ago about deploying LTE in the unlicensed band adjacent or with Wi-Fi access points. And there was a lot of concern and question about what that would do, how those two systems would coexist. And so we were able to do some modeling as well as some measurements to try and understand what impact those two systems will have on each other. And are there ways that we could deploy the two to improve the coexistence between the two? And so that's what these two surface plots here show, is that as you adjust certain delay parameters in the Wi-Fi system or in the LTE LAA system, you effectively change their probability of coexistence, or the probability that they're going to maintain some threshold. And so you can see on this plot here in the upper left that there are certainly cases where, depending on the configuration, one system is going to dominate the other, but there's also a wide range of parameters where the two can coexist, given some functional wireless performance. So this is an example of how coexistence modeling can help us address these hypothetical scenarios before devices get into the real world. As I mentioned earlier, the AWS-3 spectrum is an area where there's sort of it's a licensed band, but there's still definitely a coexistence concern. Companies paid about $43 billion for this spectrum a few years ago, and a lot of that spectrum lies in these coordination zones. And in these coordination zones, a commercial carrier, even though they bought the spectrum, they need to submit certain information to the Department of Defense before they can deploy. And the Department of Defense calculates their risk of interference, or their likelihood of coexistence, if you will, and then returns to the carrier with an answer of yes, you can deploy, or can't. And so NIST and its kind of sister organization, NASTN, the National Advanced Spectrum and Test Communications Network, was involved in a lot of measurements and analysis to try and provide some scientific data that would help DoD and the community make these go, no-go decisions. So this is essentially a very large-scale coexistence test between commercial LTE and DoD assets. Getting into some of the future topics, one of the challenges that we frequently encounter in coexistence testing is adaptive systems. Or, hey, my system, when encountered with a problem, will change its state, change its modulation coding scheme maybe, or it'll change channels, and how do we account for that in a coexistence test? And what it starts to come to is that most modern communication systems have a very large number of possible states. And we simply can't require someone to test them all. It isn't practical to go through and test every possible combination of parameters that my system may be in. And so that raises the question of what subset should we test? How do we find, a reasonable set of tests that we can do that accurately characterizes the overall system performance? And it's going to be different for LTE and Wi-Fi and for kind of each other category of system. And ideally, there'd be some kind of standardized method for selecting a subset of states or test cases. And this is an area of active research. Environmental surveys, as I mentioned, is another area of active research. The more we understand about our deployment environment, the more informed coexistence tests we can do. And so some of the questions that are of interest here are, what quantities do we need to measure? What's the distribution of sensors that we need in an environment before we can say that we've characterized it? And is there a way that we can develop some kind of database for sharing data? There's a lot of different entities that are doing these environmental studies. Is there some way that we can bring all of that data together and make it accessible? Production testing is another interesting application. We're aware of at least one medical device company that does coexistence testing at the production level, which means that every device that comes off their assembly line is tested for coexistence. And to do this, they have a custom test setup with a small shielded chamber and a fixed test sequence. And these coexistence test stations are available for purchase. And so what it seems this company has figured out is that by testing their device for coexistence at the end, before it comes off the assembly line, they can identify other manufacturing issues. And that is perhaps a good way for them to actually reduce their test time. Instead of doing all these individual components, they can say, well, I did a coexistence test, it passed, therefore it seems like everything else is working properly. But the ANSI standard wasn't really designed for production level testing. But if this is a popular application, it may be possible to tweak the standard a little bit so that it can be more useful in production type environments where you're really just you're interested in sort of rapid throughput of testing devices. My favorite future topic for coexistence testing is remote surgery. So if you have a robotic surgery suite, which is becoming more common throughout the world, and you have a 5G mobile network, you effectively have access to world-class surgeons from anywhere in the world if the wireless link works. And so in 2019, there was an example, I think the first example of this was performed in China, where the patient who was having brain surgery associated with Parkinson's disease, that procedure was being performed by a surgeon who was 1,800 miles apart. And if you just think about the mechanics here, surgeons have about 300 milliseconds to respond during an operation. And so you're talking about a network with ultra low latency. And if you think about just a signal traveling at the speed of light for 1,800 miles, and then another 1,800 miles back, you're talking about 20 milliseconds of that 300 milliseconds is just kind of eaten up in just the transit time, not to mention all of the other sort of networking overhead and application layer overhead associated with that. So this begs the question of how do we perform a coexistence test on such a system with exceptionally critical links and very tight tolerances? How do we do a measurement that we are confident enough in from a coexistence perspective that we would feel comfortable being operated on, ourselves by a robot that was controlled by somebody who was on the other side of the country? What happens if the link drops in this case, right? Does the robot know what to do? Does the system know what to do? Is there somebody locally that takes over? You don't necessarily have a lot of time to make that transition if the link drops. And so this just kind of takes coexistence measurements to the next level. From a system complexity perspective, we need to think very carefully about what KPIs we're going to monitor, and we need to think very carefully about how we perform this test. So to start wrapping things up here, everything that we've talked about so far, it's really only half the story. Coexistence is really a two-way problem. So we've talked about how well does my device perform amongst other devices, but the flip side of that coexistence question is, what does my device contribute to the environment? And this is a much more difficult test to perform because it requires some assumptions, even more assumptions, about the functional wireless performance of other networks operating in the area. And it's not currently addressed in any standards, but it is sort of acknowledged as a problem that we're going to have to address at some point. So just to summarize, why can't we all get along? Well, even if everyone follows the rules, we can still impact each other. And there's many different possibilities, many different non-standard implementations of protocols, particularly in the unlicensed band, and understanding how they all interact is difficult. Coexistence is a very challenging problem that spans a wide variety of applications, licensed to unlicensed frequency bands, medical, military, satellite, vehicle, consumer devices. It affects anything with a wireless link. So nowadays, that's a pretty big segment of the market. There's two primary standards that people can refer to when trying to address coexistence. One of them is IEEE 1900.2, and the other one is ANSI C63.27. We kind of have two categories of tools that we can use. One of them is modeling, and one of them is measurements. And this is an evolving challenge. Beamforming, adaptive systems, new use cases, 5G, millimeter wave, it all, there's some coexistence implications there with all of them, and adapting our measurement methods to fit those is a challenge and something that needs to be done. I prefer to look at it as job security. I don't think coexistence is going to be a solved problem anytime soon, so I'll have plenty to do for some time to come. So at this point, I'm happy to try and answer any questions with the couple minutes that we have left. My email address there is shown on the slide, and I encourage folks to reach out if they have some questions.
Well, thank you, Jason, for a very informative presentation. I do see maybe 2 questions you might have time to answer, and the first one was performance in a medical environment. Is this only for 60601 equipment or only if equipment is used in a hospital environment or all equipment?
So that's more of a regulatory question that I'm not really in a position to answer. Being with NIST and part of the Department of Commerce, we don't really wade into the regulatory area like that. You know, coexistence testing can apply to any device, you know, regardless of what environment it operates in. But as far as which class of devices coexistence testing is required for, that's something that the FDA would have to answer.
Okay, one more question, if you don't mind. I have not seen that this is a compulsory requirement when approving access point, radios, modems. What is the reality of this topic in the USA?
Yeah, so this is a topic, or coexistence testing in general, you know, it's not an FCC requirement. It's just something that we've seen a lot of network administrators start being interested in. You know, if I'm the network administrator for a large building and I want to bring a new wireless system into that building, I might be interested in understanding what the coexistence ramifications are. And the hope is that ANSI, you know, the ANSI standard provides a framework for that, and that we start seeing an increasing number of devices and manufacturers start doing coexistence testing simply to demonstrate to customers that, you know, we have looked at coexistence of this device, and odds are it will perform well in your situation.
All right. I do see one more question that's interesting to me as well, and then this will wrap it up.
Sure.
What's the difference between coexistence and EMC?
So this gets back to the slide that I showed at the beginning. Flip back to it. Yeah, so isn't this interference? So typical EMC testing, electromagnetic compatibility testing, looks at, you know, unintentional, you know, the effect of unintentional energy that's emitted by a source. And you're typically looking at equipment that's not intended to receive that energy at all. Coexistence testing really involves devices that are intentional radiators and intentional receivers. So coexistence testing focuses on, you know, for my device that is supposed to communicate wirelessly, how does it perform? Whereas EMC testing typically looks at the effects of other energy in the environment. You know, what is that's unrelated? How does my device perform? And so coexistence testing, again, just really looks at the intentional radiators and receivers.
All right. Well, if your questions were not answered, please send them to Jason. I think he had his email. Can you go back to where your email was listed? So if your question was not answered or I didn't get a chance to ask it, can you please send your question to jason.carter@nist.gov, and he'll be happy to answer them. Thanks goes to Jason Coder for taking time out to enlighten us about wireless coexistent measurements and challenges. Our next upcoming webinar is covering wideband millimeter wave measurements from 50 gigahertz to 1.5 terahertz on May 14th at 1 p.m. Eastern. If you haven't already done so, make sure you visit our website to register for this webinar if you are interested. On behalf of Washington Labs Academy, thank you all for attending. Enjoy the rest of your day and be safe. Thank you again, Jason.
For having me.